Please give a huge round of applause for Siddarth Jain, founder of DrDroid. Siddarth is uh, the founder, as I said, and CEO of DrDroid, which is a YC-backed startup. He's not written in the introduction. He's being humble, but yeah. And then he's going to talk about the architecture of a recent project he built on top of Clickhouse. I've seen his slides. Pretty interesting, guys. He has had a keen interest in data science and data engineering over the years. So without much ado, let's hand over to Siddarth.
The topic that we are discussing today is how do you build an events lakehouse that can support dynamic schema? And I'll get into the details of that. But before I get into that, I am the founder of a startup called DrDroid. And it's a 1.5-year-old company. We are based out of HSR layout. And we are basically, I'll skip all the non-essential slides in interest of time. So we are basically a tooling company. What I mean by that is we build tools for engineers and engineering teams to use in their day-to-day workflows. And these are some of the sample tools that we've built, and there's a lot more coming in. For instance, Kenobi is the one that's the talk about today. Alert Insights Slack bot is a Slack bot that you add to any channel where you get too many noisy alerts, and you instantly are told with a report saying that, hey, these are the 5 alerts coming from this tool, which is causing the most noise in your channels. Now, if you want to still continue and ignore it, that's okay. But if you feel like too many of your teammates are muting channels, alert channels, like anyone here who has muted an alert channel? See? Yeah. So I know, like, if it's your service, you will keep the channel on, or if you are on call, you will keep the channel on, or maybe you won't do either of the two and you'll wait for the call. Either ways, this could be something that could be interesting for some of you folks. There's another tool that we are just launching. It's called Dynamic Playbooks, wherein an engineer can write the set of instructions like you would write in an SOP document, but it's way more advanced. And I won't get into the demo. You can look at the website. You'll see it on the landing page. I'll jump to the topic that we are here to discuss. But the TLDR of the first one is that if you are a senior engineer who was ever called on an off day or during the night because nobody else had the context about that problem statement, then using this tool, you will be able to transfer the problem statement to the context to somebody else. Cool. So yeah, the counter is started now. So in terms of the team, or like, it's me here who's the co-founder and CEO. I'm a data geek, so that number addition there is also a part of it. So more importantly, my co-founders here, who's Dipesh Mittal over there in the white, he's the product is his brainchild in terms of how we executed it. So he'll be available after the talk as well for any discussion. Lot of discussion in the entire ecosystem has happened around how Clickhouse is used for logging by, from the likes of Cloudflare to Zomato to like tons of blogs that you will see everywhere on the internet. Now, what we are discussing here is the lakehouse concept. Okay, quick check here. How many of you here are backend engineers? Okay, like roughly 50%. How many of you here also consider yourself like as a data engineer? Maybe like 30%-ish. Okay, any DevOps engineers? 10% types, 10, 15%. Okay, so the concept of lakehouse is something that is evolving and is becoming a industry term. Right now, it's getting popular. The way it operates is that you have access to near real-time data with high performance on it. I'll give you an example of what it means, and that will show you how the use case actually fits in. But for instance, if on the same database, you want to run search, you want to do aggregations on events, as well as aggregations on joins between events, and you want to set up alerts on them, which means you're doing consistent recurring jobs there. So a combination of that is really hard to pull off with one tool. And that's what is the product that we've built out, and I'll walk you through how it works. Before that, a common use case that we've seen companies use us for is, let's say you have a business which has a business workflow across 10 different steps. And here, in each of those steps, you might decide to send in logs which are more business oriented. Like for instance, you look at this log here. This is effectively a log, but this does not have information about your Kubernetes pod. This does not have information about your namespaces. What this has information is, okay, this is more contextual to your business, or the labels that you're adding here, and possibly UUIDs that you're adding here. So the platform that we've been able to build, and that we'll discuss over the next couple of slides, is you can send events here. Once you send events into the platform, which can happen through multiple sources, you can do joins on them in multiple ways. For instance, just look at this one join that we've been able to do here. Right? So these are different events with a payload associated with it that is being sent here. Each of those events are interconnected between themselves using joins, and there is an aggregation that has been done on top of each of those layers as well. So the 52 there is not the count of just ledger updated event. It's the count of ledger updated where bank API called and bank response was also received. So that means that there is a flow to it, like a stateful flow to it, as well as at the same time, it is aggregating the counts as well. So doing the combination of those gets slightly non-trivial. Now, let's say we are a hacky engineer and we have been asked to build this. So how do we build this in a very let the screen share again. I'm not sure what's wrong. Yeah, so you've been asked to build it out wherein you have 2 billion events coming in on the platform. You'll have, like, let's say 150 million events per day of traffic. And then you have to have integrations with multiple tools like Segment, having a custom SDK, CloudWatch logs, right? So this is the context in which you start building out. These are the requirements in terms of, in terms of integrations. You need to support multiple channels for people to send you events, because there could be different teams that want to send you events in a different way. There are ingestion guarantees that you need to provide as a platform, that if an event is sent to the platform, it's not lost. You can provide real-time analysis or processing on top of it. You can do it asynchronously without choking anything upstream for the client. You have to provide a source of truth to the user. You have to provide fast analytics, and you have to provide features like search and metrics. So given this entire context, like, let's look at a most intuitive way in which you would probably do it. For a minimal MVP, you would probably start off with just having a HTTP direct client, which is like an API or an SDK for ingestion that for integration that people could use. You'd add a simple Kafka topic to make it asynchronous at your ingestion layer, and then you'd add a processor so that you can do the processing before adding it into a storage layer, which in our case, we started off with, just imagine, Postgres, like the easiest or the most comfortable database that most of us would be with. So we started off with Postgres, and then there's a user platform where the responsibility comes in, that the user has to do event search. They have to be able to do metric visualization, complex visualizations like the flows that I talked to you about, and also create alerts on top of it. So this architecture, we implemented it, like our team implemented it. And then what we realized was that after an event volume of beyond like 50,000 events per day, which is like nothing significant, possibly a seed or pre-seed startup, it starts to choke. And when I say it starts to choke, an aggregation call is taking like 10 to 15 seconds on one aggregation call that you're doing. Search was not possible to be done asynchronously. Reason for that is all the keys are in a single column, which is JSON type. And you need to search on a different key possibly every time. And you don't have a knowledge of the key, like the repository of all the keys that you have in your system. So that's the problem that we were facing when we decided to, reevaluate the tool. We started off evaluating how do we get beyond this 50,000 events per day. We need to hit 100, 150 million events per day, right? So then we started looking at different options, and OLAP was the most common category that we would end up latching with in terms of the tools that would be most supportive of this infrastructure. Clickhouse, Pinot, and ES were the top 3 contenders in terms of the evaluation that we did internally, the tests that we did internally. In terms of the storage, Clickhouse and Pinot were very similar in terms of the way they store data in a columnar manner. The difference did exist in terms of how they index the data, wherein in case of Clickhouse, you define the partitions. It is like slightly simpler to do it in Clickhouse versus in Pinot, you need to define custom indexes. There's a lot more configuration, which is easier when you need flexibility. But if you are a small team and you need lesser overhead, then it becomes a slightly harder task for you to implement Pinot from a index perspective. And so was the case with the maintenance that it required in terms of the fine tuning. So that was the primary reason why we decided to not go ahead with Pinot. And the other reason was, how does it operate with dynamic schema? So with dynamic schema coming into picture, in Pinot, the workflow, the way it operated was you would have to define the schema, update the table, then allow inserts into the table for that schema. And which was not going to happen automatically. It would be a manual process, so we would not be able to go ahead with it. Elasticsearch was an obvious option. We were very scared because we have seen how the mapping explosion happens when you want to map multiple keys at scale in the Elastic database. Clickhouse had an interesting feature that they call like, JSON feature that they were that was like getting slightly popular, and we thought, does it make sense to give it a shot? And that was the primary reason why we ended up sticking to Clickhouse. In terms of the stack, this the integration stack looks similar to how it was previously, except that we've added a few more sources, so the complexity in terms of managing them has increased. In terms of the ingestion, we had to create redundancies to avoid any loss of data for the client. We had to add another processing machine, because now when you looked at the workflow or the graph chart in the platform, to generate a platform like that, just like you have materialized views in Clickhouse, this cannot be done trivially with materialized views, but fundamentally we had to write a layer of metadata and data aggregation at source to enable that to happen. And this was the other thing that we did, wherein we created a source of truth in Postgres that is not used for querying in any way, only for a source of truth. We could have used S3, and there are like cost that we are burning here, but which could have been avoided. But we decided to keep Postgres because we did not have the bandwidth to transition. But Clickhouse was the one that we were using, and we were using it to power all the user features. Postgres now only drives the metadata for us. In terms of the configs of the spec that we had, this is the spec of our stack, which can easily support 150 plus million events a day in terms of ingestion. And we had a TTL, which is how fast the data is getting deleted towards the other end of 15 days in the database. So with this, any dynamic JSON schema, we were able to pull off, wherein you can write a custom query on any key within the JSON, put a search filter on it, do an aggregation on it, and be able to get the result in near real-time capabilities. Yes. So the way it happens in the JSON auto inference, the way it works is, this is the definition that I've done in Clickhouse, wherein I've defined the merge tree as my primary engine. I've done a partition by just the date. Only the date is the partition. I've added a primary key of the event name or event type ID, effectively the same. And we've added a TTL of 10 days, let's say. in this, if you see, there's a processed KV's JSON that I've added as a column here. This is the same that is coming from here, the processed events consumer. And when I do this, what ends up happening is Clickhouse. Uh, so yeah, let me just explain you how it works. Is internally, Clickhouse starts reading the payload, the JSON variable, and every key that it identifies, it starts storing it in their own metadata table. Once they do that, after that, if I add a new key, here there is key 1, 2, 3 again, but like if it was 3, 4, 5 as well, then it would create a like a union of both of these keys and store it as the entire dictionary of the keys accessible. But the way they store it internally is not as a new column, but as a sub-column. The processing of the sub-column happens, the storage happens differently, but the processing is almost equivalent of a way the column operates. So that was able to give us the power of leveraging Clickhouse in terms of using the JSON feature and being able to basically, use a dynamic schema data and store it in Clickhouse and also use it for search and aggregation at the same time. So after doing this implementation, our aggregation APIs went down to like sub 1 second. I'd say these are still fairly okay because we are doing aggregations on joins. These are not plain vanilla aggregations, but these are aggregations on joins. So it was a fairly happy experience for us in terms of the performance improvement. Search API was now synchronous. Like people did not have to wait for an async call to come back after 10, 15 seconds. This was now like a couple of seconds, which is almost similar to how a CloudWatch log insights would operate if you try to do any search on that. What we have also done is we've created a open source equivalent of our entire platform, wherein there's a, let me just open that for you. The entire architecture that I showed you on the diagram, you can spin it up with one Docker Compose YAML. This includes, so even though for our own reliability purposes, we used cloud providers for the different tools, in this stack, we've spun up everything using open source packages. There is a Clickhouse node in it. There's a Redis, there's a Celery in it. There's a Redis in it. There's a Kafka in it. So if you want to pick it up as a project wherein your team needs it internally to, let's say, put in your custom logs into it and do an analysis on top of it, you could try to install Kenobi on GitHub, and you would be able to do it within like a few clicks. So yeah, and if you're just interested to read how it works, you could go into Docker Compose prototype.docker compose YAML and read the entire way. Because here, what we've done is effectively we've created a network protocol wherein all of these different components are connected onto the same network, and then we are interacting over that network layer. So it could be something, if any of you have not done that before, that could be an interesting exercise for you to go through. Awesome. I'll just jump to the last couple of slides of this discussion. So with that dynamic data that you saw and that was flowing through, how is it actually happening that Clickhouse is able to support such fast aggregations over keys which are dynamically changing, which are not columns technically, but are sub-columns? So the way we got to know about it because of an outage that we had. Like we did not know about it until like an event that happened a month back, wherein we had a severe outage. We had no business change of any sort from any of the internal or external stakeholders related to our business. And we were really like in a stressful situation. And then we reached out to Clickhouse Cloud because they host our Clickhouse. And we spoke to them. And that's when we realized how these internal operations specifically for the JSON feature operate. The way it does it is, yeah. So how many of you are aware of how merge tree works? Okay. So let me explain it to you in a very simple explanation is that merge tree is a background operation that's happening dynamically, continuously within Clickhouse. The objective of that is to recreate partitions every few minutes or every specific time interval to make it most optimized as per the current data set. So as you add more data set into the system, it will keep doing rebalancing. Effectively, you can think of it like the way it rebalances the partitions to make them more efficient to read. And in that process, the way it works is it first checks all partitions, then decides which ones could be great for merging. And when it does the merging, there are two, the original state, which is the two different partitions, and then the merge partition. Both of them exist at the same time as a duplicated merge. Like there is a duplication that happens temporarily, and then there's a 8-minute window is what I understand, after which the older partitions are basically deleted from the system. So this entire process, in this process, they are able to look at the keys, the distribution of the keys, and decide how is it that they want to best make the partitions happen. In that situation, the issue that I talked to you about, what had happened was, because of an internal release, in case of users using the JSON experimental feature, let me remind you again. If you look at how we defined the table, the first line that you have to write in that is enable JSON, like allow experimental object type equals to 1. So because we were using an experimental object type, and that was not completely covered within the production use cases that they were looking at, and there are different GitHub tickets that talk about not using JSON feature because they are deprecating it into a new form called dynamic columns that you can read about on the internet. But yeah, there are other constraints as well. Like there are, like, you cannot have more than 1,000 unique keys. So we've had 2 billion odd events, but we've only had like 100, 150 unique keys that we are seeing within that. And we are creating multi-tenancy architecture in the terms that every new client that comes in, we put in it on a different table. So we have enough buffer, at least up to the 1,000 keys. So there is a risk of production issues. The other challenge that comes up with the usage of experimental features is that the connectors might not be so trivially available. For example, the Postgres to Clickhouse connector that is otherwise available in like one click on GitHub, if you use JSON experimental, it fails. So you will have to look at a more custom, at least until recently, we did not find one which was able to do that. I think there's one repo, but we were not able to completely test it out yet. So we had to write a custom pipeline to make that happen through Kafka, if you remember. So ideally, a Postgres to Clickhouse for JSON experimental would have been great, because under the hoods, both of them support JSON column types. But that was not possible as well. And like I said, like we had to live with this, because this outage, basically every time the duplication happens, the memory increases. And during this, there was a release that they did in January sometime, after which what happened was the memory garbage cleanup stopped happening, because of which there was an accumulation of memory on the cluster that we were operating on, and that caused us to have impact for like a few days. So yeah, I think this covers up the presentation.